Well, hello guys, Mr. G here with another video for the grade 12. This time we're going to be answering a test on Doppler Effect. So there are going to be a couple of questions on Doppler Effect. Let's see how far can we go. Remember, I don't want to make videos too long. However, let's see. Now before we start, please don't forget to subscribe for the channel so you can get the notifications, the videos, or the worksheet, etc. I post on regular basis. The first question of this test is a multiple choice and say choose the answer and write only the letter A to D next to the question, which is the correct, and it's for all the multiple choice. The question 1.1 said spectrum A represents the visible light spectrum recorded on Earth. This one is Doppler Effect in light. We didn't speak about this one, but it's quite simple, and I'm sure you at school going to do it very well. Spectrum B and C are recorded from two stars, Y and Z. So this one is on the Earth, the first one. So we have in the first spectrum done on the Earth, and the two other spectrums B and C on different stars, Y and Z. So now what we have to do here is to identify what is happening. All we have to do is to compare those lines I draw with the Earth one. You can see here that in the Earth I draw a line in each of the lines of the spectrum of the Earth, and you can see that each of the lines of the different stars shifted towards the red side, even a little bit in the one of Z, but each of them shifted. All the lines shifted from the Earth to the red. It means that they're moving towards the lowest frequency color, so it is going to be moving away from the Earth. Both of these two stars are moving away from the Earth. So let's see the question. Which one of the following combination most correctly describes the movement of the two stars? Both of them are moving away. You can see they shifted towards the red. Star Y is moving away from the Earth and star Z is moving towards, not right. Star Y is moving towards the Earth and Z is moving away, not right. Both stars Y and Z are moving towards the Earth, not right. And D, both stars Y and Z moving away from the Earth. That is the correct answer. Question 1.2. I hope that one was clear. It's very simple. You just have to see the lines where they've been shifted. So in this case, they were called red shifted. Question 1.2. The hood of vehicle traveling at constant speed towards the stationary observer produces sound wave of frequency 400 Hz. Ignore the effect of wind. Which one of the following frequencies is most likely to be heard by the observer? Now, if the vehicle is traveling towards the stationary observer, the frequency detected by the observer must be higher than the actual frequency. So from all these ones, the only one that is higher is A, and that is the correct answer. So there is always a higher frequency as it's moving toward. It's very simple. Question 1.3. A listener moves at constant velocity toward a stationary source. So in this case, you have a listener, which is a person, for instance, and that person or a listener moving towards a source. A source could be a speaker somewhere there, and that speaker is producing sounds of certain wavelength. This person is moving towards that source of sound. Okay, the frequency of sound here by the listener is higher than the frequency of sound emitted by the source. You know that. Now, what is going to happen? The wavelength observed by the listener become shorter? No, that is not correct. The wavelength observed by the listener become longer? No. More wavefront reaches the listener per second? Yes, that is the correct answer here. As he moving forward, he will cross more of the wavefront, and these lines here represent the wavefront. So more wavefront will be crossing the person per unit time as it's moving forward. That is the correct answer. Question 1.4. The siren of a police car traveling at constant velocity of 30 meters per second east emits sound wave of frequencies 700. Which one of the following best describes the frequency that will be observed at the driver of the car following right behind the police car at speed of 30 meters per second? Note, the two of them are moving at the same speed. And this one was scenario 1 when we watched the video. Please, I'm going to leave the link so you can go back. So it is not going to be greater, it is going to be equal to, because they're moving at the same speed. If they're moving at the same speed, it's like the case when they were at rest. So if they're moving at the same speed, they are actually at rest with each other relative. So here is what happened. This is rest, or moving at constant velocity, both of them with the same magnitude. So that is important. They're moving at the same velocity with the same magnitude in the same direction. Everything is the same. Question 1.5 and last one of the multiple choice. A cat traveling at constant velocity towards a stationary listener, the cat's hooter emits a sound of constant frequency as it approaches the listener. Which one of the following statements regarding the frequency of the wavelength and the wavelength of the sound of the hooter as observed by the listener is correct? So now here you know that the car is moving towards the stationary. So in this case, the source is moving towards, right? So what is happening as he moves towards, remember, he's going to start compressing the wavelength or the wavefront. So the wave becomes shorter and shorter. The wavelengths here become shorter, and as a result, the frequency detected by the listener become smaller. So both the frequency and the wavelengths are decreased? No, because the wavelength becomes shorter, therefore the frequency become higher. Both the frequency and the wavelengths have increased? No. The frequency has decreased while the wavelength has increased? No, the frequency has increased while the wavelength decreased. That is the correct answer, because the wavelength become smaller. So this is question 1. I hope you understand. It's quite simple, guys. This topic is very easy, and we are going to question 2. Now, question 2 says, a whistle of a train emits sound wave of frequency 600 Hz. So this one is the frequency of the source, 600 Hz. A person standing next to the train track hear a sound of the whistle with a wavelength of 0.5 meters. So this is the wavelength of the listener, or here by the listener, is going to be equal to 0.5 meters. Assume that the speed of sound in air, this is speed of sound, is equal to 340 meters per second. State the Doppler effect in words. Okay, so now the first question is to state Doppler effect in words. The Doppler effect is the change in frequency or pitch of sound detected by the observer because the sound source and the observer having different velocities with to the medium of sound propagation. This is Doppler effect and is very simple. You do have to learn this definition, nothing to say about that. Question 2.2. Is the train approaching or moving away? Well, if the train is approaching, then the frequency detected will be higher. If the person is moving, if the source is moving away, then the frequency detected is moving less, is getting less. But they are not giving us the frequency, they are giving us the wavelength. So let's go to the formulas real fast to see how to do. So here, guys, is the formula that help us to calculate the frequency of the wave. These formulas are going to be given to you. So this is the formula that we are going to use to calculate the frequency, and so determine if the source is moving away or towards the listener. Okay, so let's answer this question 2.2 on this side here. Speed is equal to frequency multiplied by wavelength. I show you where I did get the formula. Now, speed of sound is equal to 340. If they are giving you that one, frequency is what you are looking for, and the wavelength was 0.5 meters. So the frequency at which the sound is being detected was going to be 680 Hertz. And now if you can see here, the frequency produced was 600, but the frequency detected is going to be 680, and therefore the train is going to be approaching, it is moving towards. Okay, so for question 2.3, we come into the formulas and we take the formula for the Doppler effect. So we are going to use the formula for Doppler effect. And there is the formula for Doppler effect. Now, in this case, remember, there are 4 or 5 scenarios you can get. Please go and watch back the video. However, you always have to start with this formula in that way, in which you have the plus minus and the plus minus. So for the scenario we are busy with, in which the source is moving towards, this formula is going to be in this way, where v of sound divided by the speed of sound minus the speed of the source, and the rest of this question is just substituting. You get that the speed of the source is equal to 40 meters per second. And guys, this is the answer for this very simple first calculation, that is 40 meters per second. So let's go to the equation there. Question here, the final one is, how is the Doppler effect applied in the field of astronomy? Okay, and then how does Doppler effect apply to the field of astronomy? Doppler effect for light is used to measure the speed at which stars and galaxies are moving, either towards or away from the Earth. That is a very important application. Question 3. Question 3 says, a siren of a stationary police car emits sound wave of frequency 620 Hz. A stationary listener watches the police car approaching him at constant velocity on straight road. Assume that the speed of sound is 340. And again, let's have the data here. The frequency of the source is equal to 620 Hz here. A stationary listener watches, so the listener speed of the listener is equal to 0, watches a police car approaching him at constant velocity in straight road. Assume that the speed of sound is, and the speed of sound is given to us right here. This is speed of sound. How does the wavelength of the sound wave here by the listener compare to the wavelength of the sound produced by the siren of the police car when it approaches the listener? Only write longer than, shorter than, or equal to, and explain your answer. So this one is similar to question 1. Now what is happening? The police car, the source is approaching, so it is going to be compressing the wavelength. So it is going to be shorter than, in this case, shorter than. The wavelength become shorter than, guys. So now if the wavelength is shorter than, because it is being compressed, then the wavelength is higher. So the frequency detected by the listener is higher, and as a result, the frequency or the wavelength that the listener is detecting is shorter than. Remember, according to the formula we use here, the first formula we use here is the formula we used before. If you go there, you can see that frequency is or wavelength is equal to, let's write it in terms of wavelength, is equal to speed divided by frequency. If we rearrange this one, so you can see that is the frequency is less than the wavelength is more. So let's go back to explain what is happening here. As the police car is approaching, it is compressing the waves, so the wavelength produced is going to be shorter. As a result of this one, the frequency that the listener is going to hear is greater. Now the question is, how does the wavelength of sound detected? So because the listener is here a higher frequency, therefore it means that the wavelength detected is less. So I hope this is understand, because it's quite confusing sometimes, right? So let's say it again, because it is very confusing sometimes. As the source is approaching, there is going to be compressing the sound that the source is producing. So the source is compressing its own waves, all right? As a result of this one, the listener is going to hear waves that have a higher frequency, and because the wave have higher frequency, the wave detected by the person has a higher frequency, it means that the wavelength is shorter, and here is the formula because they are inversely proportional. Very simple, guys. It's quite simple, but it could be confusing. Let's go to question 3.2. Name the phenomenon observed. Okay, Doppler effect. Doppler effect. Question 3.3. Calculate the wavelength of the sound wave detected by the stationary listener if the police car moved towards him at the speed of 110 kilometers per hour. We cannot work in kilometers per hour. We have to convert. You are going to multiply by 1000 and divide by 3600 to convert this one. And this one will give you 30.56 meters per second. When you convert, you have to work with the conversion there. So let's say again, calculate the wavelength of sound wave detected by the listener. They're looking for wavelength, but using this formula, we need the frequency, as you can see there. So to get the frequency, we're going to use the Doppler effect equation. Okay, so we take the formula, remember, as it is, and in this case, the source is also going to be moving towards. And therefore, when you rearrange the formula, you get a minus at the bottom. The next step is to substitute what you have here. It's very simple because we have everything. We're looking for the frequency detected by the listener because we need to use it to calculate the wavelength detected by the listener. So when we substitute here, guys, this is the answer you get, and now we have to get the wavelength. With we're going to use the same formula as we wrote there on top. So speed is equal to frequency multiplied by wavelength, and then you substitute everything. 340 equal to the frequency is 681.23 multiplied by wavelength, which is what you are actually looking for. And then you get that the wavelength is going to be equal to 0.5 meters. This is the wavelength detected by the listener. So it is very simple, guys. I really think it's simple. We use the equation of Doppler 2 times just now. And then question 3.4. How will the answer in question 3.3 change if the police car move away from the listener at 120 kilometers per hour? Write down increase, decrease, or remain the same. Now it is moving away. So if it's moving away, as it showed there, the frequency is going to decrease, and therefore the wavelength will increase. That is the answer. You don't have to explain, but it have to do with the same thing here. If it's moving away, guys, what is going to happen? The frequency decreases or it becomes less, and therefore the wavelengths become greater. Write down one application of Doppler effect in medicine. There are many. I'm just going to write one or two. And the two application is to find the rate of flow of blood and to hear the heart of effects. I'm trying to get a video on an echo, which is used at the hospital, so you can see the application in a small video, how it works. How do we apply Doppler effect in real life? In this case, it's going to be in medicine. I'll try to get that video and I'll show you later on. And then question 4 is quite simple, but use high frequency waves to detect obstacles. A bat emitter wave of frequency 68 kilohertz and wavelength of 5 millimeters towards the wall of a cave. It detects the reflected wave 20 milliseconds later. This is important because then the bats emit frequencies or emit sounds, and then it detects the sound later on. So the bat become the listener and the wall become the source. So calculate the speed at which the sound wave is traveling. And let's see here, the frequency emitted is going to be equal to, this is the frequency of the source at this time, okay, or of sound. Let's write here frequency of sound. is going to be equal to 68,000 hertz. They are giving you that one there. And the wavelength is 5 millimeters. Therefore, the wavelength is going to be equal to 0,005 meter when you calculate the speed at which this sound with those characteristics is traveling. It's very simple. Speed is equal to frequency multiplied by wavelength, and when you substitute here the answer is going to be 340 meters per second. Very simple. If the frequency of the reflected wave is 70 kilohertz, calculate the speed at which the bat is approaching the wall of the cave. And now here, once more, we are going to use the Doppler effect formula there. Now, remember, in this case, the story changes because the bat is the source, but eventually become the listener because the sound is being reflected on the wall. So when you rearrange or fix this formula, become in this way. The sound of the source, of the velocity of the source is 0 because it is the wall at this point. It's a very interesting question here. Guys, the rest is to substitute, which I am going to do here at the bottom. And then the final answer here, I'm not going to show you this calculation, is going to be 10,2 meters per second. I show you a similar calculation before or how it is done, so I'm not going to solve this one. There is the similar calculation done here on top, so you can go back if you struggle to the way of doing this one. Guys, we're almost done. We're going to finish now with the light we have here. The image below shows 3 absorption spectrum observed from the same source. In diagram A, the source is not moving. In diagram B and C, the source is moving such a way that the result is a red and blue shifted respectively. So before we carry on, this is the red shifted. It means it's going to be moving away. Moving away. And the blue shifted is going to be moving toward. That is important to know because it is shifted. By using Doppler effect, explain how the blue shifted is obtained. Does the frequency of the subline in the spectrum increase or decrease from left to right? So let's explain quickly 4.3.1. Alright, so now, as the source moves towards the Earth, the wavelength is observed will be shorter than the emitted wave. That is the first important point. The wavelength is observed will be shorter than the emitted wave. Therefore, the lines that make up the emission or absorption spectrum obtained will be closer to the blue side. Remember, the blue side has therefore the higher frequency. That is how it is happening. Does the frequency of the absorbed line in the spectrum increase or decrease from left to right? Does the frequency of the absorbed line in the spectrum increase or decrease from left to right? And that one is going to be decreased because it's moving towards the red. You can see the spectrum from left to right is moving toward the red. The red is on this side. You can see it there by the red shifted. Which one of the diagram B or C is the absorption spectrum of the source that is moving away? We already looked this one. It is going to be source B. That one is the answer there. It's very simple. And the absorption spectrum is most far away object observed from the Earth show the redshift. What is that? An indication, and that one is an indication that the universe is expanding. And guys, with this one we finish the video. I hope it helped. If it did help, please subscribe for the channel so you can get more notifications and the worksheet and etc. I hope it helped. Good luck with the exams, good luck with the tests and the practice and so on. Keep practicing. I'll see you next time. Mr. G here.